So I think it will help if we think through what the basic update rule is when you're doing reinforcement learning or Q learning, and then to try to adapt it to this notion that we're representing our value function using some kind of function approximator.
Okay.
So here's a way to think about this. We've got our Q function that we're going to try to represent as some function of a set of parameters or weights, maybe let's say one set of parameters for each action.
Sure.
And what f is doing is taking a state and translating it into a set of features. We're going to feed those features and the parameters of the function into something called f, and what will come out of that will be the Q value. So this is intended to be fairly general, and we'll talk about some specific examples of this in a moment. But so let's just imagine that Q is being represented by some kind of function approximator, and here's how Q learning works. We have an experience tuple that comes in, state, action, reward, next state, and then we do an update. Now, what's the update usually? It's we try to move the value of that state action pair a little bit towards the reward plus the discounted value of the next state S prime. So that's the Bellman equation, kind of hidden in here. And the difference between that and the current Q value is the TD error. And what do we want to do with the TD error? The TD error tells us, is our current prediction too high, too low, just right? Does it like porridge? And what we want to do is change. Oh, that's the three bears, I guess. But the fact of the matter is we actually need to know the direction that we should be going. Are we too high or too low? And we want to move the parameters that represent the Q function. So a given weight, say W super A sub I, we want to move it a little bit. This is a learning rate alpha in the direction of that TD error. But how much do we move the weight? It depends on how that weight actually influences the Q function, right? So what's the partial derivative of the Q value for that state action pair as a function of that particular weight that we want to change? And we're going to change that weight proportion. We're going to change things proportionally to that gradient. So this should look kind of familiar. Does this look familiar?
Yeah, it looks exactly like the Woodruff-Hoff update rule, the things that we did with perceptrons. It's a normal kind of gradient update rule.
Yeah, right, exactly so. Right. And so when you're representing a function in terms of a set of parameters, we want to know how do the parameters impact the value that we're predicting, and let's move those parameters in a direction that makes the prediction more accurate. So this is a way that we can actually view Q learning as an update rule for underlying parameters of a function approximator.
Right. And I guess the only difference is that unlike the sort of y star minus y thing that we used to do, this is what we got on this particular step. So that's what makes a TD error as opposed to actual error. If that makes any sense? Does that make sense?
Yeah, I think that's exactly right. So when we're thinking about supervised learning, what's happening is we have some kind of output for our current input, and we'll call that y, and then we have a target output y star, and we want to change the parameters of the function so that instead of getting something like y, we get something much more like y star. So I think what your point is that this Bellman equation kind of value and this kind of current prediction do play the roles of y star and y. So this, I think, is a really good analogy. But one way that it's different is that y star, when we're doing supervised learning, is actually the right value, right? It's coming from some kind of trusted source, and it is the label. Here, we're bootstrapping, which I think is a kind of wrapping. And what we're doing with bootstrapping is we're using our current predictions as a kind of way of making a target for what our other predictions should be moving toward. So this should look a little bit unnerving, but it's not a bad idea, but it's also not clearly a great idea because instead of using real labeled data, we're actually making up our own labels using the current prediction from the Q function.
Right.
And we'll see, sometimes this can really run us into trouble, and we have to be a little bit careful to make sure that it doesn't.
Okay.
All right. So this is in a very general form. I think it would be helpful, though, to make it make more sense if we dive in and think about some particular representations of the Q function.
Okay.